All right, so today we're going to continue our iteration exercise that we started last class. So if you don't have yet, go ahead and launch that RStudio project, the 08 iteration project. As always, make sure you always launch your RStudio through that our project icon rather than just double clicking a script. So you make sure that all of your files are in the right place and the paths are working correctly for you. All right, so I'm gonna just take a quick overview of what we did last class, just so you remember. But basically, we're talking about ways that we can iterate or automate different parts of data processing. And so we're using this data set here that it was basically for each one of these points here, we pulled soil and plant root samples to count for the number of nematodes of different species and also number of eggs, both in soil and in the roots. And at the same day that these samples were pulled, a drone was also flown over this area. And so we're trying to connect here drone multispectral data, remote sensing data, with the nematode data that we were collecting from that field. I'm not going to go into a lot of detail here. We already covered this in the previous class, but basically we have 3 different species of nematodes and 5 different remote sensing bands that we're going to try to correlate with each other and see if any of these bands or vegetation indices correlate well with one of those nematode variables. So towards the end of this exercise, we're basically going to be running all potential bivariate correlations here, which is going to be a total of 150 models. And again, this is where iteration really comes into place and helping us. If you have a given task that you are repeating the same task over and over and over again, you're just changing the data set coming in, or maybe the column you're using, iteration helps you to automate that. So you don't have to be copying and pasting your code. You can just develop this iteration workflow that will basically do that work for you as far as applying the same task over different data sets. So we loaded some packages here. Make sure you load those. We loaded the data set as well. So just a reminder, it has 43 rows because we have 43 points on that field that were sampled. And then we have 18 columns that include columns related to the nematode counts and the species and whether they are in the soil or in the root system or in the rhizosphere. And then we have the remote sensing variables as well of different bands here on the same data sets. We checked the summary. We did a density plot to check the data distribution of all of these. We realized that especially the nematode-related variables are not very normally distributed. We have these long tails, meaning that we have a few points that have higher values, and that basically happens for all of the nematode variables. We talked about using the bands to combine bands into a vegetation index, and we talked about the NDVI formula, which is right there. You can kind of take a look at that. And the fact that we could, on this viz component of the formula, which stands for visible band, is where we can basically plug in different visible bands. So it could be red is the default NDVI formula uses the red band, but we could use the blue, the green, the red edge instead. And those have, they can bring us some benefits when not using the red band, but one of these others. So then we talked about just having that formula implemented right there. And then we created a function that basically we give the near-infrared band, we give the visible band, and it calculates that for us instead of you having to type out that whole formula every single time. So we created a function to do that for us. And then we basically apply that function. Well, let me actually run the chunk of the function because I'm going to need it. And then we applied that function to calculate the 4 different types of NDVI using 4 different visible bands, and then some other vegetation indices as well that were already there, just part of the paper. So just make sure you run that. We also ran this or created this function here to calculate the mean and the coefficient of variation for us of any given vector x that we give this function. So if you remember, we give a vector x, which is basically just a column in your data set. It will calculate the mean of that, the standard deviation, and also the coefficient of variation, which of the three, R has a function for mean, R has a function for standard deviation, but it does not have a function for CV, for coefficient of variation. So we're basically, the main goal of this is just to create this function that basically gives us the CV to us without we having to calculate mean and SD as intermediate steps. And then it returns to us a data frame with the mean and the CV as well. So make sure you run this function. We want to have that in your environment. And then we tested that in one column here. So we applied our function mean CV to one column of this data set. So we basically get the mean and the CV of the red NDVI column so one of the vegetation indices we calculated. We then started talking about loops. And before I get there, I just want to show you, I'm going to go off script a little bit here, just to show you something that you'll see on an assignment coming up. So if you notice right now, both the functions that we created, so the mean CV, we're just giving a vector. So if you just, let's just pay attention to this function first. So we're giving it a vector, right? So we're saying X, and this X here is basically, when we call the function, we give nematode $ RNDVI. So we're giving this vector to that function, right? We're not giving it a data frame or we're not giving the data frame itself. We're giving a column of that data frame already in a vector format. I want to show you a slight variation of this because this is going to come into play on an assignment that we're going to have coming up based on iteration, which is the following. Let's say I'm going to create here a chunk, and you can do on your side as well. Again, I'm going off script, but you can code with me. So on a Mac, Option Control I is the shortcut for adding a chunk. If that doesn't work on a PC, you can always come to this green plus C button and click on R. That's going to bring you a chunk as well. So some functions, a lot of the functions that we use natively from R, the way that they take in arguments would be, they take a data frame argument and they may take a column argument, right? So for example, if you think of ggplot, so ggplot has a data argument. So we say data equals, in this case would be nematode W, and then on the aesthetics, we say X equals to, we can just say whatever here, just trying to make a point. So it could be simple ID, perhaps. X equals simple ID, Y equals, let's say, Mel _ S. And then we do, I don't know, let's do just a geom point. It doesn't really matter how it looks like, but it's more what I'm trying to get to is how we specify our arguments in a function that is developed by, in this case, by coming from the ggplot2 package. So we give a data frame, and then we give columns inside of that data frame like this. So I want to show you how, if we wanted to adapt our mean CV to be something like this, instead of giving, so let's say instead of giving nematode $ RNDVI, if I wanted to say nematode W is the data frame, and the column I want this data to be computed on is RNDVI. So if I wanted to do that instead, right? So it will look something like, let me just copy this chunk here. I'm going to paste below. So if I wanted to do something like df equals nematode W, and then the column that I wanted to calculate the mean in CV being RNDVI. Right now, this function is not going to work. This specification is not going to work because the function mean CV is expecting X, a vector. It's not expecting a data frame, right? Now, I want to copy this function mean CV and edit it in a way that it would accept this other behavior here. So I'm just going to paste mean CV here. I'm going to call this mean CV2, perhaps. And notice what we have to change here to make that work. So the first thing is we have to change how these arguments are, what are the inputs that this function accepts. So it has to accept a df input and then a col input. Right? And so, so let's say if I wanted to, I actually, I don't know if this is going to work. Let's just try out. But if we do like df $col, I don't think this is going to work, but I still want to try just to double check. So if we run this and then we apply this function mean CV here, mean CV2 here. So basically what I did is instead of having x, I just replaced x by df $col. And then here df, when we call the function, df equals to the name of our data frame and col is the name of the column that we want to calculate this over. If we run this, it didn't quite work. It gave us an NA. So what's happening here is it's not understanding that, so it understands the argument is df and the argument is col. But these objects, df and col, don't exist, right? Basically, when we make a call to this function, df should be nematode w and col should be rn dvi and not just df and col. So this is a issue that you're going to run into every time you write a function that it has a column inside of a data frame that you want to use or you want to specify. The way that we have to fix this is you can so not on the input names, but whenever you're using those inputs in the body of the function, you have to wrap in double curly brackets like that, both arguments. Because basically what this is telling the function is whatever the user is specifying that df is, that is what I want you to bring here instead of the word df. So instead of bringing the name df, it's going to bring whatever I assign to df on the function call, which in our case is nematode w. So this should work if you wrap it around double curly brackets. Let me try. I actually did not try this before, so we'll hope that it works. Okay, he actually did not like the use of the $sign there. So here's what I'm gonna do. I'm gonna basically change this a little bit to, instead of using the $sign to select that column, I'm just gonna use a function from dplyr that is, I think, let's see, let me try something quickly here outside of this function, so if we take nematode w, and I use the function pluck rn dvi. To w rn dvi. Just try to do a dplyr select. Okay, so maybe that's using a select may work. So maybe let's try that. Do a dplyr select on this one, on this column here. We'll just try to do the same down here. Let's try that and see if that works. Okay, so it still didn't work. Let me try another function instead of select. There's a function called pull. Okay, maybe pull is what we need instead of select. I hope this will work. Okay, so this worked. So I guess the main thing I'm trying to tell you here is even though I had to do some extra work here on doing a pull of just that column, which is not it's not the main goal of what I'm trying to show. The main goal of what I'm trying to show is if you have your arguments that are going to be basically specifying a column inside of a data frame, you have to use the double curly brackets wrapped around that argument in the body of the function, so it knows to translate df. So this basically translates into nematode w, and then this basically translates into RNDVI for us. And that's how the function knows that it should not use the literal name df, but it should use the placeholding df for nematode w. That's the main concept I'm trying to explain here. So I'm going to change something. You don't have to change on your side. I just want to show you how, if we just kept this, that would not have worked. If we did not wrap around df and col in curly brackets, it would not have worked because it's basically looking for that object called df and col. And it's not finding that because that object does not exist. So if we did not wrap around curly brackets and we ran our function, it would not have worked. So we wrap in the body of the function, we wrap our arguments in curly brackets just to make sure that it is replacing that placeholding name of the argument with the actual variable that you specify on the function call. Like that. So that would work. Again, notice that before we were just giving our functions, both the mean CV and the NDVI function, we were just giving a vector, a vector by itself, right? It was just a list of values that were not part of a data frame. So we did not have to do this before because of that. Now we're given a data frame and a column inside of the data frame for this function. So for that to fully work on the body of the function, you have to wrap around curly brackets your arguments. So it understands that you really mean nematode W and not DF. I know this can be a little bit confusing, but is any question that maybe I can help you with understanding this further?
The main point is trying to understand that for the assignment, we're going to need to use those curly brackets
Yes.
because the objects are going to try and think that kind of write out text, but we want the object. So
exactly. Yep. Yeah. And so Zach's question here was, so the main point of me showing this is because on the assignment that you're going to have, you will be writing a function where you're going to need to wrap your argument names in the body of the function using the curly brackets. So it knows that you're referring to that data frame and that column and not just a df and col. Yep. And this is just a syntax, syntax way of our treating how you specify the column, the variable names inside of a function. All right, so this is new today. I know it can be a little bit confusing, but as you will be working on your assignments, I think this is gonna help you to conclude that with success, understanding this concept here. All right, so we created. So for now, I'm just gonna. I mean, this is basically it when it comes to using the curly brackets to wrap around arguments in a function. Yes. Yeah, so in this case here, if we wanted to calculate mean and CV for a different column, we would just come here and change the column. Okay, so let me just print nematode data. Let's say we wanted the sum of the nematodes in the soil. We just change the column right there. The DF remains the same, right? So the difference here is that mean CV2 is expecting a data frame and is expecting you to say this column from this data frame. Mean CV, the one that we did on the previous class, it's not expecting a data frame, it's expecting a vector, right? So if you just go back to mean CV by itself, we're just giving a vector to it. So I'm going to scroll up here. which is if you just print nematode $sign or NDVI, this is what you're basically giving to the function. You're just giving a vector. It does not have even a column name. It's not a data frame, right? There's a difference here on how we use those things in functions. And that's what I wanted to show here. All right, so we created two functions, and then we're talking about loops. All right, so a loop basically is what we're going to use when we have the same series of functions or whatever you're trying to do, that you're going to be repeating the same series of same steps for different data sets. So we're just changing the data set, but applying the same series of functions or processing steps to that. So my goal here, and our goal in this for loop that we're creating, is basically to calculate the mean and the CV using our mean CV function. So the original one, the one we created in the previous class, and calculate the mean and CV for each column in our data frame. So for that, we first created this empty canvas that the for loop is going to populate. So if you remember here, we had a variable, a mean, and a CV column, and all NA values. So what the loop, and notice again, I want to call your attention to the fact that this data frame, nematode mean CV, is a completely different object than our data frame, nematode W, the one that has the data. So the for loop is going to be calculating mean and CV on nematode W, but saving the results to another data frame. That is the nematode mean CV one that we just created this empty canvas for it to populate. All right, so we started with our loop last class. We talked about that one of the key components of a loop is an indexing letter in this case. So the indexing letter is the most common, the default one that people use is I. So we're saying I in 3, starting on 3 and going all the way to the total number of rows of nematode W. No, number of columns of nematode W is 28, I believe. I just run that, 28. So we're starting on 3 and going to 28. On the first run of this loop, the index I equals to 3. On the second run, equals to 4, 5, 6, all the way until 28. And the fact that we have an index here is what's going to allow us to basically iterate over different components of this data set and then export those results at each iteration to our object above. So the first thing that we did here is so in the end, what I want this to do is to basically give me the column that is calculating the mean and CV. So the column name and then the mean and the CV. That's what I wanted to give me at each iteration of this for loop. If I want to know the name of the columns, I need to have a list with all the column names of this data frame. So that's what col names here is doing for us. So if I just run col names here and I print col names, it is just a list with in the same sequence as they appear in the data frame of all the column names in that data frame nematode W. Because we are starting on 3, the first column that's going to be used here is mel S. If you remember, we're starting on 3 here. Normally, we would start on 1, but we're starting on 3 because we really don't care about mean and CV of the side column or the sample ID column, right? That's just not of our interest. So we're starting on 3 on mel S and going all the way to NLI in this data frame. So the first variable that we're creating in this loop is the var name. So I'm extracting what is the variable name that is being used at that iteration. So if I came here and instead said col names 3, and I just run this and I print var name is equals to mel S, because mel S was the 3rd position in that col names object. However, if I use the number 3 here, then it's not going to iterate. It's always going to give me number 3. So instead we use I and let I iterate over and change in number making sure that each run of the loop, it gives us a different a different column. All right, so now the next thing, so we already have the column name that is going to give us a mean in the CV4. So now the next step is to actually calculate the mean in the CV for the data of that column. So if you come here on the next comment, I want to call this stat sum. It's going to be the object name. It's just what I decided to call it. There's nothing special about that name. Here, we're going to apply our mean CV function. So the one that we created the first time, not the mean CV2 that I just showed you earlier. So mean CV is our function. So how do you think, let me challenge you. How do you think that we can specify here? How can I tell inside of this function and give it just a vector of values under the column that's going to be run at that point, which in this first run is going to be the mel s. But I don't want to call mel s. Remember, I want this to be iteratively, right? I want it to be able to change the column data at each run. How would you do this?
Nematode W brackets comma I.
Yes, perfect. That's exactly it. So nematode W, which is our data set. Then let's use double bracket actually and give it I. So why is that? So in the first run of this loop, I equals to 3, right? So if I said instead of I, if I said 3, and I just print nematode W 3, it basically all the values, it gives me a vector of all the values under mel s. But again, we don't want to call this just 3 because otherwise it's just going to be running on that column. We want it to be I so we can iterate over that. So on the second run, it's going to be I is going to be equals to 4. So it's going to give us the values of the fourth column and so on. Yes.
Why do we have to do double brackets?
Okay, that's a great question. Let's just change back to 3 and let's try just single brackets. That's why. So if you just use a single bracket, it gives you the column with a column. It gives you a data frame pretty much. But if you remember, our function mean CV does not take a data frame. It takes a vector. So a vector is basically a series of numbers without not being a data frame object, right? So without a column heading. And we could have tried this. So if I'm just going to go, you don't have to, so you don't get lost, but I'm just going to show you here the mean CV outside of that loop because the loop brings extra complexity that I just want to not have when explaining this. So if I had said here nematode W bracket, let's say 4, whatever column 4 is, it would have given me an error. However, because if you just print nematode W bracket 4, you're giving the whole column as part of a data frame, as a data frame object. And the way that we wrote mean CV, it does not take a data frame, it takes a vector. So if you do double brackets, it solves that. So if I'm just going to print nematode W double bracket 4, it gives you just the values under that column. So now if you run mean CV on that, it does work. So that's the reason why we're using double bracket in this case. That's a great question. Yeah. All right, so let me go back there and add here double brackets again. And remember, we want to have I, right? So every time you think, okay, I want this value to change, each time it iterates, you need an I there somehow, somewhere. So this is how we do the stat sum part of it. Now, so we have so var name is going to have the name of the column that we're doing, that we're calculating the mean in the CV. Stat sum returns to us a data frame that has both the mean and the CV of the values of that column. Now I want to append all these 3 pieces of information to, let's see here. So basically, so notice that up until this point, we only use nematode W, right? So we use nematode W to basically extract those information from it. But now I want to store these results in that other object that we created, that empty canvas object that we created, which is called nematode mean CV. All right, so let's come back here. let's call that object here. So nematode mean CV. If you remember, that object has three columns, right? It has a variable, a mean, and a CV. So I want to put the variable name that is in this object, var name, in this position. And I want to take the mean and the CV that are coming from stat sum and put the mean under the mean, CV under the CV. That's what we want this loop to do for us. So let's do first the variable, right? So we're going to call here the nematode mean CV $ variable. So we get in there and we're going to say which. So imagine that we're basically pulling this column here right now. And so we want to say, we're going to use bracket notation to say which position I want, which row basically of this column I want that variable name now S, which is the first one, to be saved as. So let's use the bracket notation. And let me ask you this. If I put I here, so let's say that we do this and I assign this and I give the assignment symbol and say var name. So var name is going to be assigned to this position here. Do you think that would work? Yes or no? And if no, why? So it's a little bit of a tricky thing of this data set specifically. If we were starting on 1 here, this would have worked well. The thing is that we're starting on 3. So on the first run of this loop, I equals 3. If I just say I here, then this var name is going to be saved on this row. It's going to start basically 3 rows ahead. It's just because of this mismatch that we're not doing all the columns of this data frame, and therefore I is going to start on 3, given the way that we specified in the loop here. So how would you fix this? What? I -1, you said?
In 1.
Well, I mean, we could, you mean here? We could change to 1?
No, not here. Then it will be the name of the
Right.
But we have to do the same name.
Right, I guess. Yeah, somebody online has a thought?
I tell us this, I think we should have I -2 because we have 2 rows.
Yes, was that Ali?
Yes,
Yes, that's exactly it. Thanks, Ali. Yes, so if you didn't hear what Ali said, we basically have to say I -2, because if on the first run I equals 3, then 3 minus 2 equals 1. So this basically assigns the var name value on the first row of variable instead. That's basically the trick we have to do here. And then we're just going to repeat this for the other variables. So nematode, now let's assign the mean, right? So nematode mean CV, $mean. Again, double brackets, I -2. So on that column, it also goes on the first position rather than the third of the mean column. And this gets the value of, so let me do something here just to show you. If I'm going to change here on the stat sum I to 3, just so we see what stat sum looks like. This is what stat sum is going to look like at each iteration. So we basically want this to be the stat sum $mean. Right, that's what we want to be assigned to this cell of nematode mean CV. And then I just want to round this to have 3 decimal points. So we just wrap that around the function round, comma 3. And that's basically it. And then lastly, we're going to do this for the CV. So nematode mean CV $CV, double brackets, I -2, get, let's use again the round function. So round of stat sum $CV, comma 3. Just going to give you a quick moment here to catch up. But basically, we're just assigning these individual components to each row of that canvas, the empty canvas that we created. So on the first round of the first time this loop goes around, it's gonna do this for the first column, which is gonna be male S, which is in the third position of nematode W. And after it gets to the end of the loop, it goes back to the beginning and add +1 to I. So on the second time that it goes around, I is gonna be equals to 4, and so on, until it stops when I becomes 28, then it runs 28 and it stops. And it stops at 28 because we specify that up here. All right, so I guess on my side, I had the 3 here just to show you what stat sum look like. I'm gonna change that to I on this level. And then just, when you have loops, it means that you're gonna be doing the same thing over and over again. And sometimes you may run into errors. Maybe something happens and it just stops and it doesn't really give you a helpful error message. So just for us to keep track of where in the loop process we are, I would just want to print a message here. At each iteration of this loop, I want to print a message. So let's use the function print, where I'm going to use the function paste here as well. And then inside paste, I want to say finished with variable. And then you get outside of the quotation marks, give it a comma, and then say var name. So we could have used just the function print if I was just printing a string, like finish with variable. But the fact that I want this sentence here to change the value of var name when it prints it every time, then I have to use the paste function here that takes the fixed text of finish with variable, but then it changes the value of var name each time it goes around. All right, so if you were able to follow along with me here, you should have everything in the right place. If you now go ahead and have your cursor in that line of code where you have the 4, just run that. Or just push control run, and then it's going to run the loop for you. What you're going to see here is that because this is a very fast calculation to do or computation, it's not demanding. It basically printed everything for you right away, like finish with variable this, and that, because the loop just went through everything and completed for you. So now, if we were to come here and print the object nematode main CV, now it's not empty anymore. It's been populated with the variable, the mean, and the CV. And each row of this data frame was created on a different run of that loop, right? So we could have tried here of what would happen if I just did I -2. I'm going to do on my side. You don't have to do it on yours if you don't want to, but just for curiosity. If I just said I, and let me run, I guess, the empty canvas first again. So it has an empty canvas to start with. And then if I run my for loop now, okay, it gave me an error here. But then if I inspect nematode CV, I basically have 2 empty rows because it started on I = 3 because that's the index that I specified on the loop. Right, so that's why here we set I -2. Just gonna fix that on my side. Rerun again. Nematode main CV as an empty canvas, and I'm gonna run the for loop again. And there we have it. We have our mean in CV for each one of the variables. Now imagine if you had many more variables, right? Maybe, we're going to start seeing data sets here as we start getting to the machine learning part of the course. We're going to start seeing some data sets with hundreds of columns, right? So imagine that you could do something like this, and it would easily calculate these things for you. There are certainly different ways of doing this. Other packages you could use, other approaches you could use, but this is one very, very easy to understand, I hope, application of a for loop to do something for you that you're just changing the data set coming in and is doing the same steps for you throughout. I hope you can, perhaps not immediately, maybe you're going to take you some time to come to this conclusion, but I hope that you can realize maybe steps in your own research where you're doing something that you're just changing the data set or you're just changing the column, but everything else is the same. That is a great candidate for you to use something like a loop, or maybe some of the other techniques we're going to be learning in this exercise to automate your process and not have to basically, imagine if you were doing this by hand, you would basically have to get the median CV 28 times, right? 28 chunks for 28 different variables that you just copy and paste and change the variable. So this avoids you from doing repetitive coding that you're always doing the same task, just changing the incoming data set. Yes, Swabir.
Yeah, I think my CV values are NA, NA, NA.
Your CV values are NA.
Yeah.
Anyone else having this problem? Okay, so if your CV values are NA, what I would check is on your nematode W. So if you just go anywhere and you print nematode W, so all of your CV values are NA,
Yes.
but the mean is not NA.
No. So it created two CV column. I think one is uppercase CV and one is lowercase CV.
Okay, so I think there's probably a typo on your side. Either you made a typo on the empty canvas or you made a typo here.
Okay.
I'll take a look at that. And if you cannot figure out, please go ahead and take a screenshot and share that on GitHub on issues, and then Aminder can take a look and help you out to see what's going on.
Okay.
All right. Any other problems? Any questions? Any thoughts? All right, so we're gonna keep moving here. Okay, so another way, so for loops and so using loops is again very popular in Python if you work with Python. In R, they do have their place, but they're not as common as in Python, mostly because of how R works. So R is a language that basically already does some iterative approaches for you behind the scenes, even if you don't ask for it. So therefore, if you code in Python, you probably are used to seeing loops a lot more frequently than you see in R. However, there are still uses in R that we could use loops, and this is one example of that. In R, there are different ways you can do loop. I guess I'm going to use the word loops, although they're not loops, but there are different ways for you to do iterative tasks in R. One of them is using loops. There is a family of functions in R that are the apply family of functions that do some similar approaches to what the loop is doing here, but in a perhaps a little bit simplified way. I particularly, when I started learning R and I started learning about these functions, I was having a little bit of a harder time understanding just because there are, I don't know, 5, 6 different types of apply functions, and they don't really follow a consistent syntax of how you specify what you want. And then at that time, I also found out about a tidyverse option for that. So I'm not going to be teaching you the apply functions. They are useful in R, they are there. If you're interested in learning, you can go and look for that on your side. I'm going to be showing you the tidyverse version of that. And before I do that, Swabir, you have a question?
Yeah, I was able to figure it out. It was a typo.
Nice. Thanks for sharing. All right. So another way of doing iterative tasks in R in a more tidyverse way is to use a family of functions that are called map. These functions here come from the purr package. So purr is a package part of the tidyverse, and therefore it follows. It's very tidyverse in the sense of having consistent syntax and also is pipeable. So we can include that in a pipe workflow, which I'm always a fan of whenever I can do that. There's, I don't know, a handful of different map functions, but again, they all have the same syntax And I'm going to introduce you to three ones that I think are the most useful for at least what I've done with my research. So one of them is the function called map that takes only one iterating element, which is x. So let's say if I just have one column or maybe one set of things that I want this function to iterate over, the map function can help you with that. And then there is the function map2, which basically takes two iterating elements, both x and y. So if you have two columns that you want that your map function to be looking at the same time while it is iterating, the function map2 is what you need. And then instead of creating a function called map3, map4, map5 to match when you have more than two iterating elements, instead they created the function pmap, which basically accepts any number of iterating elements that you may need to iterate over at the same time. I know that right now this may not be making a lot of sense, but I think it will make a little bit more sense when we start coding. The way that we use these functions in a PyFlow especially is we have to set up the groups that we wanted to iterate over. So imagine that on our loop here, the groups that it's iterating over would basically be different columns. However, this data set in this format for us to be doing iteration in tidyverse way, this data set is not tidy in the sense that I don't have one column that I can say iterate over all the values of this column. We have many columns, right? So when we get here, when we start coding this, and you're going to realize this difference, we're going to have to create groups to say within each component of this column, within each group under this column, do this. For that, we're going to use a group by that you're familiar with, and we're going to be using a new function you have not seen, at least not in this class, which is called nest. So the combo group by and nest, then followed by a map function is what is going to allow us to do iteration in a tidyverse way. It is going to be a little bit of a mind twist for you if this is the first time you're going to see group by and nest at play. And I think I'm going to wait until I get to that point to show you why. But basically, before we get to coding, my goal here is so we have all of our y variables, all of our response variables that were the ground truth data collected on this field related to nematode. I have all my x variables or my explanatory variables related to remote sensing that were collected at the same time. My goal here is to create linear models of the form y explained by x, where each time that this loop runs, y is going to be one nematode variable, x is going to be one remote sensing variable, iterating over all potential combinations of y and x, which we have 150. So that's what we're going to do here. All right, so let's get started here. So I want to, everything we're going to do, we're going to assign this to an object called nematode mods for models. So give the assignment symbol. We're going to start off with nematode W, which is our data set that has all that data. So here's something that we've done before, and I just want to kind of help you think through this. So I have nematode W. So think that all of these nematode variables that are my y variables, my response variables, they are right now in columns. What I need to do is basically pivot longer because I need to have one column saying nematode variables and the name of those variables, and then one column saying nematode values and with all the value of those columns, right? And I have to do that twice because I'm going to do that once for the nematode variables and again a second time for the remote sensing variables. Maybe this is a little bit of a crazy thing for you to think of right now, so let's just go ahead and implement so you can see what it looks like. So nematode W, if we just print, remember that we have 43 rows. So first, so add a pipe here, and let's go ahead and come after that first comment, and let's pivot longer first the nematode variables. So pivot longer, we need to specify the calls. because the nematode variables are all in sequence in our data frame, we can say starting on this, ending on this, here on the calls argument. So we're going to start on mel underscore s, which is the first nematode column, and the last one is eggs underscore r. So mel s colon eggs underscore r. And then I do want to control how the new columns are going to be named. So the column that's going to take all the column names and the column that's going to take all the values. So I come here and I say names to, and then open quotation marks. I want to call this resp underscore var. So basically resp means response variable and var means variable. And then the values to argument, I want to change that to resp underscore val, for the values of the response variable. If we just do this first, and you print nematode mods, let me just print that below here. So notice that we starting on, well, notice that first we went from 48 rows to 430. And we kept still the sample ID, yield, and then all the remote sensing data. But then if you go all the way to the right, you're going to see a rasp var, which has all the previous nematode column names, and rasp val, which has all the values of the nematode columns that previously were in many different columns. Let me take a, so this what we just did here is not new to you. We've done this before a handful of times. I just want to take a quick moment here and ask if anyone needs a refresher of what just happened, because this is going to be important for you to understand what happens next. Anyone has any questions or maybe confusion about what just happened? Okay, so notice that now I have a column that has all the name of the previous column headings that had all the nematode data. But I still have all of my remote sensing data spread out in different columns. So we're going to do again a pivot longer, but now on the remote sensing variables. So add a pipe here after that pivot longer. Come after the second comment here. We're going to use again a pivot longer, where now our calls are going to be different. We're going to have other columns here that so basically, I want to, if we just look at what nematode mods look like right now, the first remote sensing column is B, and the last one is NLI. So we're going to say B to NLI. I want to, again, control the name of the new columns. So we're going to say names to, in quotation marks, exp underscore var for explanatory variables. Variable, and then values to, I want to call this exp underscore val for the values of the explanatory variable. Now, if we run this and you print nematode mods, now we have 6,450 rows. I want to show you here just so you just so perhaps it helps you to understand what's going on. But if we come here and I do an arrange, I'm not saving this to, I'm not doing this on my pipe workflow. I'm just doing this to help you visualize what's going on. If I arrange by rasp var and exp var, so what's happening here is, let me just increase this width here so we can see together. So the first 45 rows of this data set all have XR as the rasp var and all have B as the, sorry, has XR as the rasp var and B as the exp var. So the response variable is X and the explanatory variable is blue for the first 45 data points because we had 45 sampling points in this field. If you go past the first 45 rows, now we start having all the data points where the response variable was XR and the explanatory variable was B and DVI and so on. So we have For each combination of response variable and explanatory variable, we have 45 data points and they're all running down this data set. And that's why we have 6,450 data points here. Okay, any questions about this? So this is the first time we did two pivot longers in sequence on two different sets of columns. And although you may not be understanding why we're doing this, but you're going to understand that in the next step. All right, so the next step now is going to basically be for us to create the groups. So imagine, so here's what I want to do. We want to calculate, or we want to run a linear model between eggs and the blue band, and then between eggs and each one of the bands, and then again, changing all the nematode variables from eggs to all the other ones with all the other bands, right? So we imagine that we're basically gonna run 150 models where each one of those models have 45 data points, right? Because there are the 45 sampling points on this field. So for us to create here that grouping, to create the data sets, individual data sets over which the map function is going to operate, we're going to have a pipe. If you come after that next comment, we're going to use this combo of group by. So I want to group by, in this case, two columns, the resp var and the exp var, which are the two columns that have the names of my response and explanatory variables. As you know, group by itself doesn't do anything, right? So if we just run by this point and I print nematode mods, I still have the same number of rows. And in the past, we have combined group by with summarize when we wanted to get a summary over those groups. Now, we're going to combine this with a function called nest. So if you run this, and then you print your nematode mods, so this is where the brain twist is going to come if you've never seen this before. So notice that we have 150 rows on this data set. That's because there are 150 combinations between all the response variable related to nematodes and all of the explanatory variables related to the remote sensing data. So the groups, I think, make sense. But what is going on with that data column? If you've never seen a data frame inside of a data frame, I present that to you right here. That's what basically group by and nest is doing for us. So what I want to show you, notice that that data is of type, that data column is of type list. And each cell here is saying that it is a tibble. What the heck? How come do you have a tibble there instead of a value? So let's open up this first cell here. So if I call nematode mods $data and then use bracket 1. So we basically pull out this first element to look into it. If you do that, this is what you should be seeing now. It's basically a subset of your whole data frame where you have the response value column that is all the eggs values, and you have an exp val column that is all the values of B in this case. And it is eggs and B because that is the first combination, the first row here. Oh, sorry, actually it's not eggs. It's, in this case, is males and B. So melodogeny in soil and the blue band, all the data that were related to melodogeny, soil, and blue is now confined into this single row, this single tuple under this data column. So again, if I run nematode mods $data bracket 1, you basically open up that cell so you can see what's in it. It's basically 43 rows, which are all the rows where you had data for melodogeny, soil, and blue band. And the value of those are in these columns, resp val, exp val. If I go back here to nematode mods and print it again, and let's say I wanted the second data frame here. So the second row of this data column, and I'm just going to pull that by using a 2. Now, what is changing? Well, everything is changing, But what is not changing that I want you to be aware of is the name of the columns. So now, even though the response variable values are still melodogeny, but the explanatory variable values now is another band. I don't remember now which was. So notice that the values are changing, but the title of those columns are not. So across all these 150 data frames, they all have the same overall look. They're just changing the values, but the columns are still named the same. So let's go back and print nematode mods. If you pull any of these tables and you open it up to see, they're all going to have the same column names, just different values that are reflecting that response variable and that explanatory variable that are listed outside here. All right, I know I just told you a lot of complicated things, so let me give you a moment to perhaps reflect and ask me if you have any questions. I'll wait to do what? Sorry, I couldn't.
I know that you're not gonna use it, but is there a way that you could name each?
That we could name each row?
Instead of having table, it would just give you exactly, okay, this is the data frame.
Well, so the data frame we're referring to is the description of that is basically all here.
Yeah.
Right? So it's basically the response. So if I go into the first table here, those response variable values are related to melodogeny in soil, and the explanatory variables related to the blue band.
Yeah, so but what I'm asking is, can we rename the table and just give the name of them as me or something?
Oh, okay. So if you could rename this cell.
Yes.
Okay. I've never seen that, so I don't think so. And perhaps the reason why you cannot, because here is just telling you what is the object type in that cell. Because this object type here could be different. As we're going to see as this exercise develops, this object type here is going to be something else. So this name here is just saying what is the type of that object that is stored in that cell. So it's not really a name as far as like for you to be able to call it something. It's more telling you what's the class of that object that is inside of this cell. Yeah. Okay, so I guess any more questions before we move on? Okay, I think this is a good stopping point to give you a quick break because I know that this is a lot of new information that may be a little bit of a brain twist, data sets inside of data sets. So I'm going to give you 5 minutes here if you need a break, and then we'll come back and continue the next steps, which are going to be to actually run some of the models or run all 150 models with one line of code. So let me open a new window and give you 5 minutes. All right. So our 5 minute is past. Let's resume our exercise here. If you're online, make sure you turn your camera again. Okay, so just printing again nematode mods at the level it is right now. So we have all these 150 data frames or subsets. So these 150 data frames are a subset of the whole data frame we had before doing the group by nest, right? So they're just a subset of that. So now our goal is to run a linear model, like a regression, on each one of these cells. If this was a loop, we would have to use an indexing term like I, and say for the first row, run this linear model, then the second, third, and so on. This could have been done using a for loop as well. I just want to make that clear. These are not, normally you can do both a loop or using a map function. And sometimes one is better than the other. But every time I can, I try to stick with map function just because it's, to me at least, it feels more familiar being pipeable and knowing how to work around it. All right, so now that we created our groups with the nest, let's actually go ahead and run the linear model. And this next step is where we're going to see how in the map function we set up the iteration and compare that to the for loop. So give it a pipe. Come after the next comment. Let's create a column. So we're going to have to create, so imagine now, so as you're seeing, we have a column here called data, that each cell is not a single value anymore. It's a whole data frame, right? So our goal here is to create another column on nematode mods that we're going to call this LM for linear model, where each cell is now going to be not a data frame, is going to be a linear model object. That's what we're going to do next. So we're going to have a model fit in each one of the cells of this next column we're creating called LM. So going back to the code, let's call mutate. I want to call this function LM. Now here is where we call the map function. Notice the map function does not go by itself like out in a pipe. It has to come associated with a mutate. So here we're going to say map. That's the function that we're going to use to do the iteration. The first argument of this function is what is the column name of the incoming general level data sets that you want to iterate over. In our case, that column name is data. We want to iterate over different subsets of data sets to run the linear model. So data is our first argument. Give it a comma. And now the way that this works is we're gonna call the function. So we have to start with a tilde at this point. That tilde is important. And then we're just gonna call a function like we would run a linear model. So we use the function LM in the past. I want to start off with argument data because I want to show you here how we're going to specify the iterating step of this function. So the argument data, we're going to say equals to dot x. So what happens here is on a map function that only takes one iterating element, you say first what is the name of the column that you want to iterate over. But when you make reference to that column in the function that you actually are running over, you reference to that as .x. That is just the syntax that it has. And we're just gonna use that here. The next argument of the function LM is formula. So this is where we're going to specify the formula that we want to have. So y explained by x. How do you think we should refer to our y variable in this case? Go ahead, Jonathan.
Oh, that was that.
Rest_var. Okay, so Charles said rest_var. It is a great suggestion. It's not the right one though, but it makes sense to think about it because if it was my first time, I would also say rest_var. So the actual column name we're going to use here is, I'm going to print below here the second data frame under data. Rasp val, right? So that is the column that has the actual values, right? The numerical values. So we're going to say here the formula is going to be rasp val explained by exp val. And because all these 150 subsets of data, all of them have the rasp val and xval columns, this applies seamlessly to all of them. All right, so let's go ahead and run this. If you got your, remember you need a tilde here. You need to say data equals .x, not just x. It has to be .x. And then make sure your parentheses are all closing correctly. If you now print nematode mods, this is what you see. Now we have another column that instead of a tibble, instead of a data frame, it has model fits under it. So let's just pull out this first model fit, this LM here on the first position. So nematode mods, $LM, bracket 1. This is what that is. This is basically a linear model object that you would have obtained if you just did object name, get LM, and so on. The difference is that you just did 150 in this line of code. Right, so if you print nematode mods, you have 150 linear model fits. And again, my hope here is to show you one application of these with the hopes that you can perhaps connect to your own disciplines, your own data sets, and think, okay, if I have to run, I don't know, even like 10 analysis of variance, and I'm just changing the column perhaps, or I'm just changing the whole data set, but you could use something like this, something like a for loop as well would work the same way. All right, so my goal here, let me tell you a more specific goal than what we just talked about. So we just ran 150 models. But let's say that I am screening variables here. I'm trying to see what is perhaps the best remote sensing variable to explain each of my nematode variables. So I don't want all 150 models. I just want maybe the top 1 or 2 for each one of my nematode variables. I want to select just the best. There are different ways we could do that, but one of those that I want to show here is let's make that selection based on the R-square of that model. So imagine, so just to kind of, I'm going to quickly make a code here just to show you. So on this first model where we have mylloidogeny in the soil and the blue band, if I were to show you what this linear model is doing, what is this model fit and how is that actually helping us understand this relationship, this would basically be, let me see if I can, well, I'm just going to skip the ggplot. I'm going to go straight into geom point. I want to have x equals to, let's see if I can make this in a simple way. So nematode mods, data, $1 rasp l. I think this is going to work. Let's see. And then y equals xval. It did not work. Well, I guess I can just use nematode w to show you what I was trying to show. So let's go ahead. Did you plot again? Data equals nematode w. Yes, x equals mel s, y equals b, and then a geom point. Geom point. So this is basically the scatter plots that first line is looking into. And then the linear model that's running is basically AB line method ln. Not AB line. And this is the regression line that is calculating for us. Of course, this particular relation or correlation here where scatter plot is terrible, right? There's really no, well, I guess we should have flipped. So y is mel and x is b. but it's a very, very bad correlation, right? So this R square is probably very low. And basically what the linear model is doing behind the scenes is just estimating this line for each one of those 150 relationships. And now I want to extract the R square of each one of these relationships here and use that as the metric to decide to take the best R square models for each of the nematode variables. So with that, we have to extract the R square. So if you go back to the pipe workflow we were working with, give it a pipe, and we're going to come after the next comment. We're going to use another mutate. I want to call this new column R2 for R squared. Because I want to calculate the R squared for each one of those model fits, we're going to use again the function map. Now let me show you what nematode mods looks like now. We're going to use a function. We're going to use a function here to extract the R square. I'll show you in a second. And that function requires a model fit to be given to it. So it gives us R square. So which column do you think should go here in the first argument of this map? LM, right? So LM is where we have the model fits. So LM, give it a comma, give it a tilde. So the function, there are different ways of getting R square. We're going to use the function summary. So summary of this model, and again, the model is going to be called .x. Remember that on the map function that only has one iterating argument, .x is how you refer to that after you use the tilde here. So if we just get the summary, it's going to give us a whole bunch of summary metrics. I just want the R square from that summary. So if you do a $sign R dot squared, it just returns to us the R square. And the reason the way that I found out how to sample just the R square here was basically trying to do this on a model fit outside of this loop, outside of this map function, right? So you just do a simple object with an LM, you get the summary, and then realize you can do $sign R square on that. All right, so if you run this, and now you print nematode mods, you have a new column that is called R2, and that it has a number, a double digit, floating number digit inside each one of those cells. If I come here and I pull the first one, so R2 $1, this is just the R square of that first relationship, which is a pretty low R square, like 0.0005. But now I have a column here with this metric that I can use to select the best models to keep going, like a screening approach, right? Okay, so we finished this chunk here. Let's come to the next chunk. So now, again, I want to basically only keep. So we have, I don't remember how many nematode variables we have, maybe 10. So I want to keep just one model for each one of these 10 nematode variables, which is the model that has the highest R squared for that specific response variable. So I did all these 150 models, and now I'm screening to see what was the best model to do here. So let's come on this next chunk. This is where we're going to do that. Give it the assignment symbol. We're going to start with nematode mods, which is our object above that has the nested data, the nested linear models, and the nested R square. Now, any of these columns that are nested, so data, LM, and R square, what if you want to unnest it, like bring it from that cell, bring it outside on the main data set level? There is a function called unnest. So if we come here, give it a pipe, we're going to unnest, and then you have to specify which column you want to unnest. So let's say I wanted to unnest the data, which was the first thing that we nested. If I wanted to unnest the data, you just say unnest data. And if you run it and you print it, you basically have the 6,450 rows you had originally, while still keeping the other LM and R2 columns. So anytime you have a nested column that you want to bring it out to the main level of the data frame, you do an unnest. In our case, I don't really care for unnesting the data. I actually want to unnest the R square. I want to have a column with those values there. So we just say unnest R square. That's pretty much what we need. If you print nematodes mod, notice that now your R square column is not just saying double one, it's actually giving you the cell, the value that was inside of that double one, right? Because we unnested it. And we still have 150 rows because there was only one value in each one of those nested R square cells. And now we have a list of R squares. Now it's really easy and simple for us to select the best model for each one of our response variables. Let me ask if somebody can help me here with that. I mean, the next steps here are nothing new to you, I guess, as everything else was. So if I want to select just the best model, meaning the one with the maximum R square for each response variable, how would you do that? Did you say something, Micah? Okay, we could arrange it. So we can go ahead and do that. So let's arrange by R square. Oops. Arrange and printed. So I think it is giving us, yeah, it is arranging, I think, from the lowest to the highest R square. That's what it's doing, but it's doing for the whole data set. And also, so we are arranging, so visually we can see, right? But I guess if I wanted to just subset this data, all these 150 models to only keep 10, which is one best for each nematode variable. Okay, filter. We're going to use a filter, so let's do that. So filter, what would you say here?
Next.
So max R square?
Yeah.
But yeah, okay, you're in the right path. Yeah.
Next.
Yeah, so R squared equals to max R squared, right? Is that, well, I think that's where we're going, but that's the right answer. Tifton, you have a question?
Is it okay to use a group by?
Yes. Was that Mohammed?
Yeah.
Yes, thanks, Mohammed. Yes. So if we go ahead and run this filter right here, and we printed. So what is happening here is that it actually is giving us 150 models, is not truly filtering because nematode mods was previously grouped by here, by raspvar and expvar. So it's keeping those 150 groups and is giving us the best for each one of the groups. But right now the groups, each row is a group pretty much, right? Each row is a combination of raspvar and raspvar and expvar. So we have to basically, before doing this filter, we have to change our grouping, right? We have to group by, so Mohammed was saying that, thanks Mohammed. Group by which column? Raspvar.
Raspvar.
Yes, raspvar, right? That's the column that we have our nematode variables. So raspvar and then filter. If you print it now, you end up with 13 actual rows because we had 13 nematode variables. But then you can see here for each one, so now each raspvar is only appearing once, and that R square is the R square of the best R square for that specific nematode. And then you can see here, for example, for Melodogeny and eggs, red edge was the best variable. However, for Heterodera and soil, green NDVI was the best one. So you see that your XVAR, EXPVAR is changing because we're only keeping the one that was the best for that response variable. So we just went from 150 models to 13 on a very quick screening process of what's the best model. Any questions about this? All right, so now we know what's the best model, even though they are not very good. As you can see, I think the best R-square we have is 0.14 for melodogeny in the roots, explained by a simple ratio index, but still the best model for this data set. What if now I want to create a ggplot and actually show each one of these scatter plots with the model fit for all of them? You know, maybe if you were not in the iteration class, you would do this 13 times in 13 different chunks and just change the data. But as you're probably guessing, we're not going to be doing that. We're going to do that through iteration steps. So let's do that in this next chunk here. So we're going to start this chunk by giving the assignment symbol. We're going to call this object where we have just the filter models with the best R-square. So nematode mods cell is the one that we're starting off with the next chunk. Let's give it a pipe. If you come on the next, after the next comment here, we're going to be creating ggplots. But remember that when you have a nested structure, you have to use the map function, which has to come with a mutate. So we give a mutate. Let's call this column splot or scatter plot. We're gonna use here. So here's well, let me start simple and then I'll increase complexity. So let's just use a map function. If I print you here the nematode mod cell, and I want to do a ggplot of this scatter plot for each one of the 13 models, what column do you think we need to give in the map function? So if we give R-squared, then that's the only point that we have. Mother, did you say something else? R-squared. So think about
Rest bar.
Resvar. Okay, that's also not it. So think of which one of these columns actually have the values that we can show in these scatter plots. Data, right? The data column is the one that has it. So we give the data here on the map function. Oops. Give it a couple of line breaks. Let's always need a tilde here. And then we're just gonna call ggplots. So very, very common as before. So in this ggplot, we're gonna say data equals to .x, right? Because this .x is connecting to that column data that we're specifying on the map function. And then here on the AES function, our x is going to be, so let me show you again what one of these data look like. So come here, nematode cell, $ data, the first one. This is what ggplot is seeing right now. So which column do you think should go on the x-axis? What do you think, Priscilla? What we want to do is cut a plot of the relationship that we ran in this model, in these models, right? I guess I'm giving you the answer right there. But I wanted y'all to see it, right? So let me come back again. So this is the data set that ggplot is seeing at this level. So we can put on the x-axis, let's put exp val. And then on the y-axis, rasp val. If you come outside of the AES and outside of the ggplots, let's add a plus and call it geom point. That's going to be our scatter plots. I do want to add here a geom smooth as well. So it shows us a linear model going through those points. So method, and then we have to change method equals LM because the default method of smooth is a LUS type of model, which tries to be a wiggly line. We just want a linear model so it matches our actual linear model that we ran. All right, so if you run this, and now we call nematode mod cell plots and just print that below here. We have all of our 13 columns or 13 rows still, but then our last column now is a GG column, is because each one of those cells is a ggplot. It's not a data frame, it's not a number, it's a full-blown ggplot. What if I want to see the first one? So let's add a $sign, call SP-plot, and just pull out the first one. This is what that first cell under SP-plot looks like. If we pull the second one, is going to, well, let's pull the last one, because I think the last one had the highest R-square. Let me see here. Yeah, so the last one is number 13. So if I pull number 13, this is that R-square. This is that scatter plot of that relationship. Now, if you wanted, you could basically print all of these ggplots by just not giving an index here. You could just say object name $sign splots, and it would basically print all 13 for you if you wanted. I just try normally not to do that because sometimes it can take a lot of space, but you could do that. All right, so let me pull here the first one again, the first SP-plot or S-plot. So it looks like this. It has RASP val on the y-axis and EXP val on the x-axis. Now, if I pull the second one, or maybe any of them, let's put the 7th one, it has the same RASP val and an EXP val. The problem here is if you were to export these plots, you would not know which plot is related to which experiment, exploratory variable, and response variable. You just don't know at this point. But we can fix that because that information is on the main level of the data set. That information is right here. RASP var and EXP var, those values are the ones that are being used for that first scatter plot. So this information is somewhere, it's just not right now in our plots. So what we're going to do here is I want to I think I was one step ahead of what I was going to do. So let me take us one step back again. So let's say that I wanted to show, so right now, let's just live with the fact that if we just print the plots, we don't know what is the experimental exploratory variable, what's the response variable. But let's say that for now, my goal would be to just add the R-square as a text on these plots. I want to have written each one of these ggplots, what is the R-square value? If we look again on the main level of the data frame, so nematode mod cell plots, we have again our column of R-square. So we know we have this information outside of the nesting, right? So on the main level of the data frame. How can I bring in this column here, this value into each one of those plots? So this is an example where you're going to be iterating over 2 columns because you're using the data column to actually create these scatter plots. And then you're bringing the R-square value as well into that ggplot call because you want to say that let's say you want the title to be R-square is this value. So this value of R-square lives outside of data, right? It is not inside of this tibble. It is on the main level of the data frame. So we need to iterate over 2 columns. To do that, we're going to come here on this map function. Instead of using map, we're going to use map2, which then takes a second iterating column, which in our case, the name of the column is R2. So data, R2, give it a comma. The way that we can incorporate this information into this plot here is if you come after the geom smooth, you add a plus. We're going to call the function labs, which we've used before. The function labs has many arguments we can change here. I want to change the subtitle, and I want to say that the subtitle is going to be equal to that R-square value. Now, a couple of things have to happen here. Every time you have a numerical value, or maybe not just a numerical value, but you have a value that is changing for different things, and you want to show that as text, we have to use either the function paste or paste0 to allow for that number to change on each iteration of that text. Let's use the function paste. I want to add here a quotation mark and just say R square and colon. So it has the R square colon text every time. And then we give it a comma. And if I want to bring in that R square value in this string of text, I just say dot y. So remember, on a map only, we just have a dot x, which is the only one iterating element. On a map 2, we have 2 iterating elements, where the first one is called dot x and the second one is called dot y. That is just the way that it works, it's just the syntax. All right, if you run that, and now you pull out any one of these plots, it's gonna have a subtitle saying R square colon and then the value of that R square. So this was an example where you are iterating over 2 columns. One is giving you the data for the scatter plot. One is giving you the R square that you're bringing as a subtitle of that ggplot. All right, any questions at this point? Okay, so we're gonna do our last step here, which is gonna be the most complex of this exercise. So these scatter plots, so we have the scatter plot, we have the model fit, we have the R square, but then I want to bring back, I guess, the problem I brought you earlier, which is the fact that we don't know which response variable and which explanatory variable each one of them are, at least not if you look in the plot only. We have that information as part of the main data set, right? That is, we have 2 columns that are describing that, but we do not have that information in the plot at this point. I don't know that this first scatter plot is mylloidogeny in the soil and red edge band. So now we're going to bring that into the plot as the next step. The problem now is that I'm iterating over data, R square, rasp var, and exp var. There are 4 iterating elements that I want to bring into this next part of the code. Because of that, we're not going to be able to use map or map2 because they only take 1 and 2 iterating elements. We're going to have to use a function called pmap, which is one that allows you to bring any number of iterating elements into your iterating function. So if you give this a pipe and come after that comment, let's call mutate again. I want to call this splot_better as our column. Let's give it an equal sign, and we're going to call the function pmap. So pmap, I guess, unfortunately, has a little bit extra complexity on how to determine what are the iterating elements. So it's not just say 1, 2, 3, 4, like you were doing for map and map2. We're going to have to wrap that around a list function. So let's open here a list function right there. And here I'm going to give the argument names that I want to. Before we had to call .x and .y. Now you can name it whatever you wish. So I want to call this .df to be the data frame. And .df is going to be equal to the column data. Give it a comma. If you want a break line, just to make it easier to see, I want to call .r2. So this is going to be the placeholder for the R square column that is a column in our data frame. Give it a comma. The next one I'm going to call .rv for response variable. And this is going to be equal to the rasp_var column. Give it a comma. And lastly, we're going to call .ev for explanatory variable. This is going to be equal to our exp var. Now, come after the parenthesis that closes the list function. So the first one after exp var, give it a comma. You can break line just to help you visualize. And then another difference here on the pmap function is we have to call this function and say again just the name of the placeholder objects. So .df, .r2, .rv, .ev. This is just, I guess, so you initiate those those placeholder names in the functions that come afterwards. Now, after this function, make sure that you close the parentheses. Now we're gonna bring in our ggplot. So pretty much, I wanna ask you to come here and copy that ggplot that you just did above. You can leave the tilde out because PMAP does not use the tilde for some reason. But just copy the ggplot until closing the labs function and paste right after here the function. So the difference now is that data, instead of being equal to .x, is equals to .df because we established that name above. Our XP val and RASP val are still the same. So notice here that we do need to create the placeholder values for variables outside of the data frame that we're using for the scatter plots. Variables inside the data frame that we're using for the scatter plots, we're just called for their actual names. So we still have our geom point, still have our geom smooth, still have our labs for the R square. Now here on the labs, if you come right after, let's see. So if you come right after, in between the first and the second parentheses, give it a comma and break line. So you are still inside labs. That's what I'm trying to do, is still be inside of labs. And I just want to say x equals dot, let's see, our x here is our explanatory variable. So x equals EV, comma, y equals dot RV. So that's all we had to change here. So notice that now on this plot, we're changing for each row in the main data set, we're changing the data coming in, the R squared value coming in, the response variable coming in, and the explanatory variable names coming in. All of these are changing simultaneously on this plot. So if you run this, and if you were able, like I was not, to, oh, I used the Y. Okay, yeah. So you are also having this issue. So we're just copying this code from the previous chunk where we called the second element .y. Now we don't have a .y. What would you put in place of that .y?
.r square.
.r square, right? So .r square, that's what we want. So if you run this and you got all of your parentheses right, it should have worked. Now, if you print the whole object, we have another column for splot better. That is also a ggplot. Each cell has a ggplot. Let's print the first one. So splot better bracket 1. So notice now that we have this scatter plot, we have the R squared as subtitle, and then we have what is the title of that response variable and the title of that explanatory variable. So now these plots are looking better. They're still not professional looking, right? We're not going to get into that because that's not the goal here. But the goal was to just show you how you would iterate over many elements that are outside of the nested columns. That we would use PMAP for that. Something that I've used this just to give you some example in the past. So I had a data frame that, well, this is actually one of your data sets. And maybe we're going to do this in this class, I don't remember, but we have a data frame with daily weather data starting on January 1st all the way to December 31st. And each row of this data, well, so imagine that you have 365 rows for each site, but then you have 1,000 sites. So you do a group by site and nest. So now data set has one row per site and has a data column where the data column has all 365 days of weather data for that site and that year. Now you also have planting date and harvest date outside of the nested data set. So you want to only keep weather data starting on planting dates and ending on harvest dates. You can use a PMAP for that you give the data, and then you say filter days of the year less than planting or more than planting date and less than harvest date. You can do that as well fairly easily. So just another application here. All right, so the last couple last chunks here. So now that we made all these plots, that we have the 13 plots here that represent the best regression we could have had for each one of the nematode variables. Let's say that I want to export those plots to file. So, well, I guess that this last print, the first plots is basically what I did here. So I'm just going to copy this code and paste here. So you have there is just that first plot. But now I want to export that, all of them. We're going to use a package that I think you already have. And if you don't, you can just go ahead and install it. But the package is called Grid Extra. So library Grid Extra, just so. Oh, I'm actually in the wrong chunk. Sorry, I guess on this chunk here, what I was trying to do was just to print all these plots in the same chunk. So you just do something. You call the object name and then the column you want to print without giving any indexing number. And it's just going to print all 13 plots for us. And then we can visualize all of them together. Now, let's say you wanted to export all these plots. That's what we're going to do here on the library Grid Extra. So we're going to do something and assign that something to an object first. So this object is going to be called all plots. Give it the assignment symbol. This Grid Extra package has a function called mArrangeGrob. That's the one we're going to use here. The first argument that it takes is what is the column in your data set that has all these plots. So we call the data set name nematode mods cell plots, and then $sign splotbetter. That's where we have the plots we want to export. And then I just want to say here how many number of rows and columns I want them to be arranged. So n row equals 4, n col equals 4. If you run that, it did not work because I did not load library Grid Extra first. And then if you print it, it would be this. It's basically putting all of them together. And now if we want to export it, we're just going to use ggSave. We're going to say plot equals all plots. And the path here, that's ... / so we get outside of code. We go inside of outputs. Let's call this allplots.png. So if you run that, and then you come here on the side, on your files tab, on the output folder, click on all plots, you're going to see all of your plots exported. Whew. All right, that was a lot of new information. I made that sound. Yeah, it was a lot of new information. I'm sure that your brains are like wanting a break from all this. But just to recap here, so we created two functions, right? So one was to calculate NDVI. The other one was to calculate the mean and the CV. We then iterated over the data set to calculate the mean and the CV of each column using a for loop. We then use the function map to iterate over data sets on a tidyverse way. So I hope, I'm not going to show you how to do both of these things with a for loop and tidyverse, but you can do both of these iterative exercises using both approaches, right? But then when we have one iterating element, we use map. And if we had two, we use map2. And if we have more than two, you have to use pmap for that. All right, so save your script, go on your Git tab, stage your script specially. Click on the check mark. Let's say here on the commit message, finished iteration, commit, and then push. Okay, we have a few minutes here. So I do want to first, I want to open up to check if anyone has any questions. I know we went through a lot of complicated stuff. Maybe you don't have questions because you're confused. But if you do have questions, I'll be glad to help you out understand this concept. All right. Yes.
The two ggplots, real quick.
You mean here? Yeah. Okay, so while we have still a moment here, I do want to tell you, I have two assignments for you. One of them is extra credit, meaning if you want to do it, you're welcome to. If you don't want to do it, you don't have to. You're not going to lose points. If you do decide to do it, you're going to have over a week, I think a week and a half to do it. It's going to be the repeated measure exercise. Basically, you're going to have to first watch, well, to do in class, what we would have done in class, it's a 5-hour recording exercise. Just as a heads up, if you do want to do it, you're going to have to put 5 hours into the coding part. And then there is an assignment in the end with some very simple questions. But this is, again, I know that not all of you have repeated measure analysis, but if you do and you want to do that, I think it's a really nice exercise to learn how to implement repeated measure. So I have that option for you. Let me come here to my teaching tab. So my teaching folder. So it is in 2025 DSA, I already pushed that. So it's assignment 7, repeated measure. There's a lot of instructions there. You can follow those instructions and do it if you want. And again, if you do decide to do this assignment and you get a bad grade, it's not going to hurt you. But if you get a good grade, and that can be used to replace a grade of another assignment that was mandatory that maybe you didn't do as well. So an opportunity there to improve your grade of a previous assignment, if you get a good grade here. So again, the repeated measure one is not mandatory, is extra credit. You do if you want. If you don't want to do it, you don't have to. You're not going to be losing any points. But then we also have assignment 8, which is mandatory for everyone, and is going to be about iteration. So you can open that. I'm just going to open the instructions here to walk you through that very quickly. I don't know if it opened. Let's check again. Well, I have no clue where that is opening. Let me close this and try again. Okay, so this assignment here is going to ask you to create a I think I did not push the right one. Well, okay, I think I have a typo here on data set, but basically, and I'll fix that once I get back to my office. But basically, you're going to be using the data set that we used on the data wrangling exercise. That was a soybeans data set that we had potassium, potassium fertilizer rates as the treatments, and then potassium leaf concentration. You're going to use that. I'm asking you here to basically create a function. This function, the goal of this function is going to be for you to just give a data set and what goes on X, what goes on Y, and the function gives you a ggplot, a box plot based on ggplot. So first you create that function, and then you're going to create some iteration. So then you're going to apply that function in an iterative way using the map family of functions and create 4 different box plots using your function and using mapping functions as well. Yeah, I noticed I had small typo here on the instructions. I'm just gonna change that once I get back, and then you should be good to go. And this is gonna be due by March 18th, 11:59 p.m. So 5 days from today. This is not a lot of work. You don't have to watch anything. If you're doing the repeated measure one, I think that one is due on March 25th, so you have more time. Also because it is more involved. You're gonna have to watch 5 hours of recordings. Okay. That's all I wanted to, all I had to for you today. I think Amrinder probably opened the attendance already, so make sure you claim your attendance. And yeah, if you, well, on this one here, you're gonna have to work on, if you have issues, feel free to help each other through GitHub. I do expect you to do these things. If you're using ChatGPT, you can use it for troubleshooting, or like if your code is given issues or trying to learn, but don't just copy and paste from ChatGPT. That's not going to help you to learn. And that's the goal of this exercise. All right. Well, if you claim your attendance, then you're good to go. I'm going to stick around for a couple of minutes in case anyone has any questions.
Dr. Bestos.